Hello everybody, this is Mika Seppälä. The convergence or the divergence of a series may be established by comparing that to certain improper integrals. This leads to the integral test, a very useful method in studying series. As an application of the integral test, I also consider the harmonic series and so that it diverges. Consider the series summation k from 1 to the infinity ak. Interpret this series geometrically in the following way. Over the interval from 0 to 1, place a rectangle of height a1. Its area is also a1, the first term of this series. Over the interval from 1 to 2, place a rectangle of height a2. Over the interval from 2 to 3, place a rectangle of height a3, and so on. Now the areas of these individual rectangles correspond to terms of this series summation k from 1 to the infinity ak. And it is obvious that the series summation k from 1 to the infinity ak converges if and only if the combined area of these yellow rectangles is finite. Now assume that these numbers ak are given by a function f. So assume that ak equals f at k, where f is a decreasing function as shown here in this picture. Since f is decreasing, it follows that the domain under the graph of the function f contains all these yellow rectangles. Therefore, if this domain under the graph of the function f has a finite area, it follows that also these rectangles must have a finite area. That leads to the integral test statement, theorem A. Let f be a positive decreasing function and let ak be fk. Then the series summation k from 1 to the infinity ak converges if the improper integral from 0 to the infinity f of x dx converges. This is now immediate on basis of the previously shown figures. As an example of the use of the integral test, we saw that the series summation k from 1 to the infinity 1 over 1 plus k squared converges. This series is defined by the function f of x equals 1 divided by 1 plus x squared in the sense that the terms of this summation k from 1 to the infinity 1 divided by 1 plus k squared are given by this function f. The function f is positive and decreasing for x positive. Therefore, we may use the integral test, and we observe that the improper integral from 0 to the infinity dx divided by 1 plus x squared is limit as b goes to the infinity of the proper normal integrals from 0 to b dx divided by 1 plus x squared. Now this function 1 divided by 1 plus x squared is easy to integrate. An antiderivative is arctangent of x. Therefore, this improper integral from 0 to the infinity dx divided by 1 plus x squared is limit as b goes to the infinity of substitution to arctangent of x from 0 to b. So this is limit of arctangent of b minus arctangent of 0 as b goes to the infinity. Arctangent of 0 is 0. Limit of arctangent of b as b goes to the infinity is pi over 2. So the value of this improper integral from 0 to the infinity dx divided by 1 plus x squared is pi over 2. And this means that the improper integral converges, and hence by the integral test also the series summation k from 1 to the infinity 1 divided by 1 plus k squared converges. The series summation k from 1 to the infinity ak can be estimated also from the below by an improper integral under certain circumstances. Assume that these ak's are given by a positive decreasing function f, so that ak equals f at k. Interpret the series summation k from 1 to the infinity ak geometrically so that Over the interval from 1 to 2, place a rectangle of height A1. Over the interval from 2 to 3, a rectangle of height A2, and so on. These are the yellow rectangles shown here in this picture. The area of a yellow rectangle corresponds to a term of this series summation k from 1 to the infinity ak. This geometric interpretation of this series summation k from 1 to the infinity ak differs from the previously used one in that we have moved all rectangles to the right. That's the only difference. But now it is obvious, since the function f is decreasing by assumptions, that the union of these yellow rectangles contains the domain under the graph of the function f from 1 to the infinity. Therefore, if the domain under the graph of the function f from 1 to the infinity has an infinite area, it follows immediately that also this series summation k from 1 to the infinity ak diverges. This is the second part of the integral test, theorem B. Let f be a positive decreasing function and let ak be fk. The series summation k from 1 to the infinity ak diverges if the improper integral from 1 to the infinity f of x dx diverges. On basis of the previous considerations, this is now immediate. These improper integrals may converge in both cases, and if that happens, we can conclude that the improper integral from 1 to the infinity f of x dx is at most the sum of the series summation k from 1 to the infinity ak, and this is at most the improper integral from 0 to the infinity f of x dx. This double inequality is illustrated by these two pictures below. Now this can be generalized, and we can start the summation instead of from 1, we can start it from any positive integer m. On the right, we integrate from 0 to the infinity f of x dx, that is from 1 minus 1, and on the left we integrate from 1. Therefore, if we replace the starting value of the summation index by the positive integer m, we observe that the improper integral from m to the infinity f of x dx is at most the sum of the series k from m to the infinity ak, and this, on the other hand, is at most the improper integral from m minus 1 to the infinity f of x dx. This is a handy error estimate that tells us what kind of an error we make when we estimate the sum of a series by a partial sum. The series summation k from 1 to the infinity 1 over k, that is the series 1 plus 1/2 plus 1/3 plus and so forth, is called the harmonic series. This is an important series. Partial sums of the harmonic series are computed here in this table. The sum of the first 100 terms is 5.18 and so forth. The sum of the first 1000 terms is 7.48 and so forth. The sum of the first 10,000 terms is still a little bit less than 10. The sum of the first 100,000 terms is a little bit over 12. The sum of the first million terms is 14.3 and so forth. And the sum of the first 10 million terms is still less than 17. So it seems that the partial sums for the harmonic series grow very slowly, and one might think that the harmonic series therefore converges. A simple application of the integral test shows that the harmonic series summation k from 1 to the infinity 1 over k diverges. Namely, this series is defined by the function f of x equals 1 over x. this function is positive and decreasing for x positive. Therefore, we can apply the integral test. And we observe that the improper integral from 1 to the infinity dx over x equals a limit as b goes to the infinity of the integral from 1 to b dx over x. Now this integral from 1 to b dx over x is easy to compute. It is substitution to log of x from 1 to b. Therefore, the improper integral from 1 to the infinity dx divided by x is limit as b goes to the infinity, substitution to log of x from 1 to b. This substitution gives log of b, because log of 1 is 0. Therefore, we conclude that the improper integral from 1 to the infinity dx divided by x, which is limit as b goes to the infinity, log of b, diverges, because this limit is not finite, this limit is the infinity. And since this improper integral from 1 to the infinity dx divided by x diverges, we now conclude by the integral test that the harmonic series summation k from 1 to the infinity 1 over k also diverges. The harmonic series have interesting applications in construction. To build a cupola, the builder lays bricks above each other and displaces them as far to the right as possible, as shown in this figure, without making the building collapse. Now assume that the bricks have the length 2 units, maybe feet or meters, long bricks. If the displacement of the highest brick is 1 unit, the brick will not fall, because then the center of the gravity of the highest brick lies above the next highest brick. Now, if you compute the center of the gravity of the 2 highest bricks, you observe that the displacement of the second brick can be 1/2. And for the nth brick, the displacement can be 1 over n. So this cupola will reach a large distance to the right, because the harmonic series diverges. These bricks can reach any distance from the base. This is useful when building buildings that need to support themselves. A prime example of a large cupola is the cupola of the Cathedral of Florence. This cupola was designed by Brunelleschi and completed in 1436. The shape of the cupola does not suggest that the stability of this construction would be based on the divergence of harmonic series. However, that plays a role also here. The French philosopher Nicole Oresme, who lived from 1323 to 1382, demonstrated that the harmonic series diverges. Therefore, this fact was certainly known to Brunelleschi when he designed his cupola. In this video, we have considered a series, summation k from 1 to the infinity ak, which is such that the terms ak are given by a positive decreasing function f. If that is the case, then the series summation k from 1 to the infinity ak converges if the improper integral from 0 to the infinity f of x dx converges, and if the improper integral from 1 to the infinity f of x dx diverges, then also this series diverges. If all these improper integrals and series converge, then we have the double inequality that the improper integral from 1 to the infinity f of x dx is at most summation k from 1 to the infinity ak, and that is at most the improper integral from 0 to the infinity f of x dx. This double inequality generalizes, and if we start the summation from some value capital M, then we get a new series, truncated series. We have summation k from capital M to the infinity ak, and this is at most the improper integral from m minus 1 to the infinity f of x dx, and at least the improper integral from m to the infinity f of x dx. This second double inequality is handy when we need to estimate sums of series, which cannot be computed directly.